Okay, so we were looking at this following statement that for every, so we have this theorem that we want to prove. For every set of formulas sigma, there exists for every set of formulas sigma if sigma is consistent, then there is some sigma prime superset of sigma such that sigma prime is maximally consistent. So that was the theorem that we were proving. And I don't remember how far we got. Did we finish the proof, or we were almost there? So we constructed, the proof was that we started with a list alpha 1, alpha 2, alpha n of all WAFs over some fixed set of propositional variables, and constructed a sequence of sets of formulas such that sigma 0 was sigma, and for all I, sigma I proves alpha I, or sigma I proves the negation of alpha I, and sigma I is consistent, and sigma I plus 1 is a superset of sigma I. So we constructed this sequence of formulas. We showed that we can carry out this construction for all I. And finally, we defined, let sigma prime be the union over all I from 1 to infinity of those sigma i's. And we saw that if we take such a union, although they are ordered by inclusion, by increasing inclusion, the union can contain new things because it's an infinite collection of sets. Now it was not hard to show that. So now we have this claim. We want to show that sigma I is maximally consistent. So the first part we already showed. For every alpha, either sigma prime proves alpha, or sigma prime proves the negation of alpha. The second claim was also clearly true. Sigma prime is a subset of sigma, but we were left with the third claim, which is sigma prime is consistent. And once we show this, we have finished our theorem. And the proof was that the proof relies on the fact that every formal proof is finite. So since every formal proof is a finite sequence of formulas if sigma prime proves alpha and sigma prime also proves the negation of alpha for some alpha, we can find some sigma, some say I star, for which sigma I star contains all the sigma prime assumptions used appearing in any of these two formal proofs, the proof of alpha and the proof of neg alpha. Therefore, sigma I star already proves alpha, and sigma I star already proves not alpha, contradicting this construction that every sigma I is consistent. So that was the end of this proof. I think that's we ended the last lecture.
No, we actually started proof with theorem how consistent sigma is satisfiable.
What?
We started proof for the theorem
Okay.
how consistent sigma.
Okay, so this was the proof of this, and you say we got even further, right? Okay. So next we want to go back to our connection between syntax and semantics, and we want to define, to prove the completeness theorem and the completeness theorem says that every consistent sigma is satisfiable, and the proof, so for the proof, the problem is that you have a sigma that you know it's consistent. Are there any questions?
Kind of. How do you, like, couldn't there be infinitely many formal proofs? So how do you know, even if they're finite, if there's like infinitely many, doesn't that mean there wouldn't be an I star that caps?
No, because we don't talk about infinite formal proofs. I just look at if sigma prime is inconsistent, then for some alpha it proves both alpha and neg alpha. So I'm just looking at these two proofs. This is one proof and this is the second proof.
Oh, you're just looking at one.
Just looking at these two proofs. So each of these two proofs is finite. Right? So there is sigma I star that contains all the assumptions needed for these particular two proofs.
Okay.
But then we will get it is sigma I star is already inconsistent itself. And our assumption here in our construction was that every sigma I was consistent. So this is a contradiction. Okay, so the problem is we have a consistent sigma. We don't know how to define a truth assignment. So the idea is, so the first step, pick, using the last theorem, pick sigma prime, which is a superset of sigma, which is maximally consistent. And then we have to define a truth assignment, define second step, define a truth assignment V of sigma star sigma prime. V of sigma prime as follows. V sigma prime of P for all or any propositional variable P, V sigma star of P equals T if sigma star proves P and false otherwise. So we can all, no matter what sigma we have, we can always define this V sigma. At this point, we didn't use anything except which property of sigma prime did I use here in order for this to be a valid definition? Yes? No, I don't need completeness. I use, you see, if you have any, if I give you any sigma, right? Say sigma is just P1. So what will be V sigma? For every propositional variable, it will be true if this guy proves it and false otherwise. So V sigma will look like this. To P1, it will assign the value true because it can prove P1. For P2, what value will it assign? False, because it cannot prove anything else. Right? So it's a well-defined truth assignment. It just gives few T's and lots of F's. Right? So which property of sigma prime do I still need to use in order to make sure that this is a valid definition?
You haven't used that it's maximally consistent.
So this one is not maximally consistent, and it's well-defined assignment. That's what I demonstrated here, right? So what can go wrong with such a definition? What can go wrong with such a definition is maybe I will have a double definition for the same P. So could it be? Oh, it's okay. If I wrote here false if sigma prime proves not P, then I will need the consistency, right? But here I just wrote otherwise. So what happens if sigma prime is inconsistent? What will happen if it's inconsistent? What will be the truth assignment? Everything true. If it's inconsistent, the truth assignment will be everything true. Because it can prove every P, everything will be true. So it's always well defined, because here we said otherwise and not if it proves the negation. So we are in the game. But now we have to show, what did we want? We want to show that sigma is satisfiable. So we want to show that this sigma prime satisfies sigma. Satisfies every formula in sigma. And maybe there are no propositional variables sigma. So here we have the main claim. For every formula alpha, sigma prime proves alpha if and only if V sigma prime of alpha is true. V hat, because it's not a variable. Okay, so Now, we have to, of course, decide how are we going to prove this, and we can rewrite it. I mean, if I have for every formula alpha, then what's the natural way to prove it? By structural induction. Structural induction on all formulas alpha. Right? But so we'll do it proof of the claim. By structural or generalized, how do we call it? Structural induction or generalized induction? What? Generalized induction? Generalized induction on the set of all formulas. Right? But now we define the set of all formulas. What is it? It was I of, here I have propositional variables. And here I have the four operations and, or, arrow, and not. You remember? That was when we started talking about propositional logic. That was our definition of the set of all formulas. But for the sake of formal proofs, we had a propositional logic that only had these two. We know that these two is an adequate set of connectives. Everything I can express with this guy, I can express with just these two. So for the sake of formal proofs, we said it is simpler to discuss propositional calculus only over these two operations. So this is the set we need to do induction over. Yes?
But isn't our well-formed formula a syntactic notion?
A syntactic notion, but I'm saying the syntactic notion, we will redefine it. The syntactic notion is just using these two formulas. I'm saying this syntactic notion, I mean, sure, it's just a matter of symbols. Why do I care if it's an adequate set of formulas? Because I want that this syntactic notion will capture everything that you can capture with propositional logic. I am looking forward to the semantic. I'm kind of predicting the semantic. So I want to pick a syntax that will allow me full semantics. Okay, so now we want to do induction on this. So what is the induction basis? The induction base. So I want to show that for every formula alpha something happens. And I am doing induction over this structure. So what is the base case? What is alpha? Yes. Right. So alpha is P for some propositional variable P. And we need to show that sigma prime proves alpha if and only if my truth assignment satisfies P. So anybody wants to give it a try? We have this definition of our V sigma prime, and we want to show that for a propositional variable P, sigma prime proves P if and only if V sigma prime gives its value true. Yes?
That's the exact definition of our truth assignment.
You just fell into the trap that I digged. Okay, so one direction. So we need to do here if and only if. One direction only, right? So if, we need two directions. If sigma prime proves P, then by the definition of V sigma prime of P is true. But we need if and only if. So now we need what happens if sigma prime does not prove P. I want to show you that then you will get false. So now we have to be a little bit careful. So what happens if sigma prime does not? Oh,
Yeah, definition.
still definition. You're winning. Okay, if sigma prime does not prove P, then again, okay. Then still the definition. Well, so where did something went away?
There's the other direction.
No, but if
No, if I do if yes, then yes. If no, then no. Then I get two directions. Right? If I want to show A if and only if B, then it's enough to show that if A, then B, and if not A, then not B. Right? So this is if A, then B, and if not A, then V sigma prime of P is F still by our definition. Okay, so we can carry on. Yeah, I'm not, right. Okay.
There's no trap with you.
There's no trap so far. I mean, if it's inconsistent, you see, then this case will never arise.
yes.
So we are still okay. But we will get to it in a second. Okay, so now we need to do the induction step. So for induction step, we have to take care of both of these operations. So we assume the claim holds for alpha and for beta, and need to show it for neg alpha and for alpha errors beta. Okay, so let's have the first case. First case, neg alpha. So assume we have to show both directions. So if sigma prime proves neg alpha, I want to show that it's going to be to get the truth assignment true. So how can we argue? You see, it's not a propositional variable. I can't go back to the definition. But what I can use is my induction hypothesis. So I know the claim holds for alpha. So now I'm going to invoke the consistency. So now, by the consistency of sigma prime, if it proves not alpha, sigma prime does not prove alpha. That's exactly the consistency. Right? But now I can use the if and only if of the induction hypothesis. Induction hypothesis was for alpha, sigma prime proves alpha if and only if it gives it true. So if it didn't prove alpha, what does it tell me about the truth value? Right. So by the induction hypothesis, so by the induction hypothesis, V sigma prime of alpha is false. And now, so by the truth table of neg, vega b hat of sigma prime of not alpha is true. So are we done with the case of negation? Not yet, even not by the case of negation. Because this was only one direction, we need if and only if. So now, the second direction, So the second direction, then assume that sigma prime does not prove not alpha. What will I do now? I want to show if it proves not alpha, it will get the value true. If it doesn't prove not alpha, if and only if, it will not get the value true. So what do I do now? Because it's complete, what happens if it doesn't prove not alpha? Right. So then, by its maximality, sigma prime, if it doesn't prove the negation of alpha, sigma prime proves alpha. And now what can I invoke? The induction hypothesis. So, because on alpha we know everything. By the induction hypothesis, V of sigma prime of alpha is true. So, by the truth table of the negation, V sigma prime of not alpha is false. So I showed both directions. If it proves not alpha gets true. If it doesn't prove not alpha gets false. So here for the negation, I finally used both the maximality and the consistency of sigma prime. Now what do we need to do? We need to handle the case of the other connectives. So this is second case. We have to handle the formula alpha eros beta. So again, I mean, assume, so first direction, if sigma prime proves alpha eros beta. Now, how do we get out of it? I mean,
Use our, I believe it's question 1b in our assignment 2. We have proved that it's sigma prime proves either not alpha or beta.
Deduction.
what?
So sigma prime proves not alpha or beta, one of the other, or maybe both.
You think it's true?
Yeah. It's not?
It's not. I mean, say for example, I mean, only, what was the assignment? I don't remember what the question was. What did we assume about sigma prime? So anybody has the assignment, why should I?
Question. There was no proved questions on the assignment.
What?
There was no proof.
There was no proofs in the assignment, it was only about semantics.
Implied.
So it could have been a similar thing about logically implies, but not about proofs. Yes.
Yeah, that's true, that's true.
So that's something where you have to be very careful about. The assignment was about logically implies, about semantics. This is syntax. We cannot confuse the two. Not yet, not before we have the completeness theorem, yes.
Read deduction theorem on that?
The deduction theorem will have that sigma prime union alpha proves beta, but then I cannot use the induction hypothesis on sigma prime union alpha. I can only, right? So we are going to just distinguish here two cases. So we will distinguish two cases. So let us consider whether sigma prime proves alpha, or because if it doesn't prove alpha, it proves the, I mean, either prove alpha or proves the negation of alpha. So I will say I will show that either if it proves the negation of alpha, then by induction of hypothesis, alpha gets false. No, if it proves the negation of alpha, What? Then everything is fine. Okay, let's let's do it. So if it proves the negation of alpha, then sigma, if it proves the negation of alpha, then I have to show by deduction theorem that sigma and alpha proves beta. So assume, so either sigma prime proves alpha, right? In which case, if it also proves alpha arrows beta, sigma prime also proves beta. Because if it proves alpha arrows beta and it proves alpha, then I can use modus ponens. I'm in the syntax, right? And I get it proves beta. And now I will use the induction hypothesis and what the induction hypothesis will tell me. Because now I'm down to knowing what is happening with alpha and beta, right? So now I'm using the induction hypothesis. So this step is clear. We assume it proves alpha arrows beta. If it proves alpha, since it also proves alpha arrows beta, I can do modus ponens and show that it proves beta. Now, using the induction hypothesis, we get induction hypothesis that everything is nice for alpha and beta, that V sigma prime of alpha is true, and V sigma prime of beta is true. So by the truth table of arrow, V hat sigma prime of alpha arrows beta, I have true, true, it'll be true. Okay? Now, if it doesn't prove alpha, otherwise, what can I say? If it doesn't prove alpha, with all the assumptions that we have, what can we say? What?
That means the V of sigma prime of alpha has to be false.
If it doesn't prove alpha, right? But we don't even need it, right? If it doesn't prove alpha, otherwise sigma prime does not prove alpha. So by the induction hypothesis, again, we know everything about alpha. V sigma prime of alpha is false. So by truth table, V sigma prime of alpha arrows beta, if this gets false, then this is true. The induction hypothesis was it proves alpha if and only if the assignment gives alpha true. So now I'm using the only if. If it doesn't prove alpha, then the assignment cannot give it true, so it gives it false. If the assignment gives alpha false, we know that false arrows everything gives me true. So what are we left with? I mean, we are almost there. We are almost done. Still one step. Anybody can tell me which is the missing step yet? Yes?
If sigma prime doesn't prove A arrow B's,
Right. So now we are, because we need to show if and only if. So if it does, then we're done. If it doesn't, we should show that it gets it, give alpha arrows beta false. So now, finally, assume sigma prime does not prove alpha arrow beta. Okay, so if it doesn't prove alpha arrow beta, I claim that it doesn't prove the negation of beta. Did we show it? I think that, oh, this is the one thing that we are all the time missing, right? I think that this is the one so there is one formula that I promised you that will show a formal proof of, and we're still missing. I want to show you that it is provable that from not beta we get alpha arrows beta. Okay, so let's just assume it. Put it on our list of formal things to prove. I think we've already encountered this because we needed it to show that we can always extend to a maximally consistent set. So let us assume that we did this formal proof. Now we can finish the proof of the compactness of the completeness theorem. We said, okay, so either assume that it doesn't prove this, right? Then sigma prime cannot prove beta. How do I know that sigma prime cannot prove beta? Because if it does, but we can use the axiom beta arrows alpha arrows beta and MP to get sigma prime does prove alpha arrows beta, which is contradiction to this. So if it doesn't prove alpha arrow beta, it cannot prove beta. Because proving beta, then we have this axiom beta. Which axiom is this? Beta arrows alpha arrows beta? The first axiom. And then modus ponens. So if it proved beta, it would prove alpha arrows beta. It didn't prove alpha arrows beta, so it doesn't prove beta. It doesn't prove beta, then what do we know? If it doesn't prove beta, by the maximality, no. It doesn't prove beta. Beta is false. So what if beta is false? It doesn't really tell you that alpha arrows beta is false. Right? But it proves not beta. Proves not beta, and then I will use this to get a contradiction. But can I go with semantics completely? If it doesn't prove, okay, so we say it doesn't prove beta, then beta is false. So I need to get alpha arrows beta.
Yeah, and you have that semantic right there.
Yeah, I think that thing you wrote might not be correct. The thing you're having us assume, because if beta is false and alpha is true, that isn't a tautology. That's false. When beta is false.
Oh, okay. Okay. If beta is false and alpha is true.
True, then you get true arrows false.
Shai. Okay, cool. Okay, good, very good. I mean, you should send me an email for 3 bonus points. Okay. Okay, so let's just finish it. So what do we have? So we know that sigma does not prove beta. Therefore, sigma proves, okay. Therefore, by the induction hypothesis, by the induction hypothesis, we get that V sigma star of beta is false. Right? V sigma star of beta is false. Okay, so now what do we get? We get that we have to show that this is false. So we need to show that alpha is not false. Oh, come on. I shouldn't get strangled here.
It proves both alpha and beta. Maybe that's slightly easier.
What?
If you claim that sigma prime proves alpha and sigma prime proves beta, it might be easier.
If sigma prime does not prove alpha equals beta.
Yeah, that's exactly the same because you are using counterpositive.
Yeah, okay, so what do you suggest?
Sigma prime proves alpha and sigma prime proves beta, both of them.
How is it related?
Because that's the backward proof. This is if sigma does not prove alpha arrows beta, then you get sigma.
No, then I'm talking about truth assignment, right? We have to do if and only if on truth assignments.
Yeah.
Right? So we said if it doesn't prove this, then it gives beta the value false. We want to show that it gives this false, so the only way it can go wrong is if it gives alpha the value false, right? Mm-hmm. So if we need to show that V sigma prime of alpha equals beta is false. Since we know already that V sigma prime of beta is false, our claim holds unless V hat sigma prime of alpha is false. Okay, now we are done. Now, by induction hypothesis, this implies that sigma prime cannot prove alpha. So, by maximality, sigma prime proves not alpha. But I claim that now, if it proves not alpha, then it proves that alpha arrows beta. And that's a contradiction. So, if sigma prime proves not alpha, then sigma prime proves for any x, then sigma prime also proves alpha arrows beta, and we get a contradiction. So we are done. For the last step that I want to ask you how to do it because I think you can do it. So how do I know? So we did a small step here. We said, so here we have a subclaim. If sigma prime proves not alpha, then sigma prime proves alpha arrows beta. Any volunteers for this? So the trick is use deduction. Sigma prime proves alpha arrow beta is equivalent, so it suffices to show that sigma prime union alpha proves beta. Right? But sigma prime already proves not alpha. So we know that this is if and only if sigma prime union alpha union not alpha proves beta. Because the not alpha, I get it from the sigma prime, so by monotonicity, If I add it, I didn't add any power. Right? We assume that sigma prime can prove not alpha. If it can prove not alpha, then anything it can prove, you can already prove, anything you can prove with not alpha, you can already prove just with sigma prime. And we know that from a contradiction, we can get a proof of anything. That's what we've already shown. That if you assume alpha and not alpha, it can prove beta for any beta. So we are out of we finished the proof. So it was a lot of playing games with if and only if, all the directions. I mean, you have to go over it and make sure that you can digest it. Because as you see, the midterm is next Thursday. The midterm is going to be very much like the assignment, like the 2 assignments. And you saw in the assignments that you need a lot of kind of considerations of this type. And I also...
Did you say that the midterm is going to be like the 2 assignments or 2 assignments?
No. The midterm is going to be much shorter than 2 assignments.
Good.
It's going to be shorter than even a single assignment.
Good.
Okay? But the type of the questions are going to be similar, not the same as... Right. Okay? So we have the completeness theorem. So what do we get from the completeness theorem? So the completeness theorem is pretty amazing because if we go back to our syntax semantic table, we can now complete this table fully. So if we look at our syntax semantics table, syntax, semantics, now we can complete it fully, the full corresponding between the 2 columns. So here in the syntax, I had alpha provable, and here I have alpha is a tautology. And recall that this was soundness. And now I claim that we can get this. And similarly, we had sigma proves alpha, which means sigma logically implies alpha. Here we had soundness. And I claim that now we can get this. So this is what we want to now focus on. Let me do it with 2 lines. What have we already seen? Let me continue the table. We already saw the following, that here I have sigma is consistent, and here I have sigma is satisfiable. And here we've already proved both directions. We saw that consistent implies satisfiable. That we showed just now. And satisfiable implies consistent. We've seen already in earlier classes. So here we have a full match. And we will also show a full match of sigma maximally consistent with sigma maximally satisfiable. So in the remaining time, we'll just fully complete the table. We don't need any more big effort. It all just follows through from what we have already. So let's start. I want to show you that if this direction we already did, this was soundness, right? And it's clear that it suffices that I do the second one the first one will follow. How does the first case follow from the second case? By taking sigma b the empty set. So it's enough to show this the second case. Right, so that's the completeness direction. Completeness theorem for all set for alpha and any set of WAFs sigma if sigma logically implies alpha, then sigma proves alpha. And the proof now is obvious, will become very simple. Assume by way of contradiction that it doesn't. Otherwise, which means sigma does not prove alpha, then sigma union not alpha is consistent. That was part of our proof of the construction that we did. If sigma does not prove alpha, then sigma union not alpha is consistent. So by our last theorem, by our last result, sigma union not alpha is satisfiable. So sigma does not logically imply alpha. Because if this is satisfiable, means that I have a truth assignment that gives all of those true. And what value does it give to alpha? False. Which means it doesn't logically imply alpha. Okay, so we got, by just doing this construction of taking a sigma, showing I can extend it to a maximally consistent, using the maximally consistent to define a truth assignment, I got something pretty amazing. For example, I got that the first line, that any tautology has a proof. Without doing anything constructive about giving you a tautology and asking you to show a proof. I give you any tautology, say alpha arrows beta or beta arrows alpha. I think it's a tautology, right? This is a tautology for every alpha and beta, or some other terrible tautology. I wanted to show that it's provable. We don't have to worry about formal proofs now. All we have to show is say, oh, that's a tautology. I can check it with a truth table. This theorem tells me it's provable. So it was kind of a miracle. We have a set of axioms. We had a very strict notion of formal proof. But to show that things are provable, we almost didn't use any of it. Use very little component of it. We only needed the ability to prove one or two basic tautologies, and by those basic tautologies, we could prove our theorem, and now I can take any tautology and know that it has a formal proof. So that's one very nice aspect of this result that we just showed. Now let us go and finish. So we have done these two. Now let us finish this maximal consistency. And that will also give us you remember that last time I was asking for an example of a maximally consistent set. Right? And you suggested that I'll take the set of all propositional variables. Now I can show that maximally consistent. So let us do this, show that maximally consistent is equivalent to being maximally satisfiable. So assume, so we have here a claim. If sigma is maximally consistent, then it is maximally satisfiable. Proof. So sigma consistent, in particular, sigma consistent implies sigma satisfiable. That is just what we just did. This was the proof that we just did. Consistent implies satisfiable. We constructed this set an assignment V sigma prime. So consistent implies satisfiable. What about maximality? So for the maximality, since for every alpha, sigma proves alpha, or sigma proves not alpha, we get by which theorem? By, I wanted to fill it in, that sigma logically implies alpha, or sigma logically implies not alpha, so it's maximally satisfiable. By which theorem do I have to use it? Here. Soundness. Just sound, right, just extended soundness. If it proves alpha, then it logically implies alpha. If it proves not alpha, then it logically implies not alpha. So we got that being maximally consistent implies being maximally satisfiable. What about the other direction? So assume if sigma is maximally satisfiable, I want to show that it is maximally consistent. So first, satisfiable implies consistency. This we already had before. This is just by the soundness. And for the maximality, so given any alpha, since for every alpha, sigma logically implies alpha, or sigma logically implies not alpha, we get by completeness, sigma proves alpha, or sigma proves not alpha. So sigma is max consistent. So now we have full translation between semantic notions and syntactic notions. Which means that in the exam I'll have to sometimes tell you, try to do this without using the completeness theorem. Because otherwise everything seems to be easier with the semantics than with syntax. We also get, we also get an alternative trivial proof to the compactness theorem. So do you remember what was the compactness theorem? Yes?
Sigma is satisfiable if and only if it's finitely satisfiable.
Right. So just recall the compactness theorem said sigma is satisfiable if and only if sigma, every finite A subset of sigma is satisfiable, right? But now we can do it like this. We have sigma satisfiable, so just an alternative proof. Sigma satisfiable. We know that this is if and only if, by completeness and soundness, sigma is consistent, now we have shown in our last proof that this is if and only if every finite A subset of sigma is consistent. So this is what we just showed when the problem that you were bothered with, right? Because if sigma is inconsistent, it proves alpha and not alpha. Each proof is finite, so I can collect all the finite hypotheses and get the finite A, which is inconsistent. So inconsistent means there is a finite inconsistent set. And consistence means every smaller thing is consistent. And then by soundness and completeness, we can get every finite A subset sigma is satisfiable. But I guess you cannot really read what I'm writing on this corner, right? Okay, so let me just rewrite it here. So I just want to demonstrate how easy our life becomes once we have this soundness and completeness. We can choose for every problem whether we want to solve it in the syntax realm or in the semantics realm. So the compactness is easier to solve in the syntax. So we have sigma satisfiable. I'm saying this is what we proved now. Soundness and completeness gives us sigma is consistent. Now I claim that this is if and only if every finite A subset of sigma is consistent. And what I claim is that this argument was implicit in our last proof. Because we showed that if sigma is inconsistent, sigma proves some alpha and not alpha. The proofs are finite, so I can collect all the hypotheses and get the finite A that will already show alpha and not alpha. So if sigma is inconsistent, there is a finite A which is inconsistent. On the other hand, if sigma is consistent, then every subset is consistent. So this is just by the finiteness of proofs. Since the proof is finite, if I get a proof of inconsistency of alpha and not alpha, I can get it from a finite subset. And now we will use the soundness and completeness to get if every such finite set is consistent, then every finite set is satisfiable. So every finite A subset of sigma is satisfiable because consistency and satisfiability are interchangeable. So if we follow this diagram, we get the compactness theorem. Sigma is satisfiable if and only if every finite subset is satisfiable. So we can either have a direct proof like we did a month ago, or rely on the soundness and completeness, go to the syntax, and in the syntax, this statement is very simple. Just follows from the finiteness of proofs. Okay, so we're basically done with propositional calculus. What we have had, I mean, there's one more. One more non-trivial result that I promised you at the beginning. At the beginning, I was saying, when we started talking about logic and propositional calculus, I told you propositional calculus looks very simple. What can we say about it? It's all about p arrows, not P arrows Q, all kind of things like that, we can very easily check what's true, what's false, what is satisfiable, what's not. And I promised you that there are going to be complete non-trivial statements about this, and I kind of demonstrated it with all the things we did now. This matching between syntax and semantics, consistency, satisfiability, maximal consistency, maximal satisfiability, and so on. There was one thing that I promised, one non-trivial result that I promised and didn't show, and I think I'll just keep it for the assignment, and that was the interpolation theorem. But it's not, since I'm not going to do it now, I'm not even repeating it. You remember something like that? It was something like that. If sigma logically, Craig's interpolation. If sigma logically implies alpha, then I can find some beta in between. Anyway, I said I was not going to repeat it. There's one more thing that I promised and didn't do. We'll do it in the assignment. So what is our plan from now on? So now we kind of finished all the discussion with propositional calculus. We almost understand everything about propositional calculus. There was one big open question that we don't know about propositional calculus, and what was it? Remember? Because it looks like propositional calculus is an easy game. Once we learn the rules of the games, we can do everything you want. The one open question, one big open question, and that was, is there a polytime algorithm to figure out if a given alpha is satisfiable or not? That was this question, which is P versus NP. So it's a big question in computer science. It's open. It's about propositional calculus, but it involves computation. It talks about polynomial time algorithm. So it is a question that relates to propositional calculus, big open question, but it's about the existence of efficient algorithms. And other than this, it seems like we know everything. There is one more interesting related open question, which is a very close question. This is maybe a good thing to finish the propositional calculus part with. And this is the question of lengths of proofs. Lengths of proofs. So one thing, this is a very interesting topic. So the question is as follows. Assume that you have a correct statement. If the proof is too long, maybe we will never know that it's correct, not because there is no proof, but just because the proof is so long that we'll never be able to write it up. Or even if it is written up, we will never be able to read it. Right? Because what does this completeness theorem tells us? It tells us for every tautology, there is a proof, right? But it doesn't tell me how long the proof can be. So maybe I have some very simple tautology, such that the proof requires, I don't know what, 10 to the 10 to the 10 to the 10 to the 10 many lines. So I have this cute tautology, but my formal proof will be like this. And this is not just a kind of a toy question, because in mathematics it's a real issue. I mean, there are proofs we know, and I think we have now one candidate like this, some kind of a big open question in number theory that some Japanese guy has a proof, claims that he has a proof, and the proof is, I don't know what, 500 pages, and nobody has been able to verify or refute the proof so far. And this is just a small game. What is 500 pages? Why won't we have proofs like this? So one interesting question is, do we have any guarantee on lengths of proofs? So to state it more the logical question could be, is there any bound to the length of proof? if we look at it from the point of view of computer science, we would like to ask, is there a polynomial P of n? So some polynomial P of n such that for every tautology alpha, there is a formal proof of at most p of the length of alpha lines or lengths. Let's call it length. Now, this is a very natural question. Can we come up with, are there any short tautologies that require long proofs? Right? Now, why do I mention here polynomial and not just any other bound? That notice that if I use a different proof system, if my proof system is truth tables, then I know that any tautology has a proof which is at most the size 2 to the size of alpha. I always have a truth table of this size. So if my proofs are truth tables, then I do have a bound which is exponential in the length of alpha. Right? So this is one open question. And another open question is, I mean, maybe our proof system is not good enough. I only had 3 axioms. It's very inefficient. We saw how difficult it is to prove. But we can ask, does there exist any sound and complete propositional proof system with this property? So maybe the proof system that I used is really very inefficient and may require big proofs. But is there a different one that will not require big proofs? We know that the truth table as a proof will require exponential size. But what about this? So it turns out that, I mean, both of them are open questions in computer science. Both of them are questions that people have been struggling with for many years, and they don't have answers, which is pretty amazing. This question relates to another question in complexity theory that this is equivalent to the question NP equals co-NP, but I will not get into it. For people who took complexity, NP, or in other words, it is, if we translate it to understandable language, it kind of says, you see, here we ask, can we verify satisfiability in polynomial time? And here we ask, can we verify that you are a tautology in polynomial time? Do you have short verification of tautologies, which is different than being satisfiable? I mean, if a formula is not satisfiable, then the negation of this formula is a tautology, right? Alpha not satisfiable if and only if the negation of alpha is a tautology. So checking satisfiability and checking tautologies are related. But checking for tautologies is very similar to having a proof. Because if you have a proof, then you show that it's tautology. Anyway, so this is another big open question in computer science. So we finished I just mentioned 3 big open questions in computer science that relate to propositional calculus. One is the famous P versus NP. Do you have efficient algorithm for satisfiability? And the two others relate to the notion, really interesting notion of lengths of proofs. Is our proof system efficient, or does there exist an efficient proof system? And that relates to other classic questions in computation complexity. Okay, so next time on Thursday, we will start our new logic, first order logic, and we'll go through the same sequence of results with the new logic. Thank you.